Section 10.3 is the beginning of polar coordinates. So usually we use an ordered pair called coordinates, and they're in the Cartesian coordinate plane. So we talk about the distance from the x-axis and the y-axis. But in Section 10.3, we get to a coordinate system that was introduced by Newton, and it's called the polar coordinate system. It starts with the polar axis, and so you're going to be thinking unit circle, which is the right way to go. So it starts with the polar axis, which is a ray. The point in the center is called the pole or the origin, and then the axis is usually drawn like this. Now, the way that we graph is we start at this ray, and we go to some point. Now, our ordered pair in this case is r comma theta. R is our radius, and theta is our angle. So if you were to look at it here, say this is some point P, r comma theta. So this is theta, the distance, and this is the length r from the origin O. Now, similarly, we would have back here, this would be negative r, so this would be the point negative r theta. So we could come up with it that way, because a negative radius means it goes backwards. Polar coordinates are usually graphed. There is polar graphing paper. Your book doesn't use it, but let me show you what that looks like. So this would be polar graph paper, where this is your main axis right here, your initial ray. So then you're asked to plot the points in a polar, whose polar coordinates are given. So for example, 1, 5 pi over 4. Let's do a couple of these. 1, 5 pi over 4. Well, we know that this over here is pi, just like in your unit circle. This is 0 and 2 pi. So 5 pi over 4 would be right here, 5 pi over 4. And the radius of 1 would be this inner circle here. So this would be theta, and that would be r. So that would be how you graph that point, 5 pi over 4. And we draw a direction arrow to indicate that that's what we have. You can label your direction arrow theta, or you could label it as 5 pi over 4, either way. The second one, let's say we have 2, 3 pi. Just like in your unit circle, you start at your initial ray for the origin, for the polar axis, and we go to 1 pi, 2 pi, 3 pi. So we come all the way over to here. We don't make that circle quite that big, but we can come all the way over to here and label it 3 pi. Let me erase the first one. Let's just erase it all. This is our polar axis. So we would go 1, 2, 3 pi. And the radius in this case is 2. So we would come to right here. And this would be 2 comma 3 pi. So the next one is 2, and we have negative 2 pi over 3. Negative 2 pi over 3. So just like in trigonometry, our negative angles go backwards. So we're going to start at the pole axis, and instead of going counterclockwise, we're going to go clockwise. And we're going to go to 2 pi over 3. So 2 pi over 3 from the negative angle would be I have to think it through. So this would be pi over 3. This would be pi over 6. And this would be 2 pi over 6, which is pi over 3. Negative. And then we have negative pi over 2. And we have negative 2 pi over 3. And then this would be negative 5 pi over 6. And negative pi. So negative 2 pi over 3 is over here with the radius of 2. So we would draw our initial axis, our pole, and draw our point. And this is 2 pi over 3. Now, polar graph paper is not something people tend to carry around with them. So just keep that in mind. The last one is -3 and 3 pi over 4. So we start at our polar axis and we're going to 3 pi over 4, which is over here. So we're going out to a radius of 3, 1, 2, 3, only it's a -3. So we're going to hit that same line and come down to -3 here. So this is our -3, 3 pi over 4. Your book does it dotted. Let's follow that format so that you've got it. So they would do this line here and then do the dotted line here. So you can see how to graph. So the polar coordinates, not bad graphing. Remember that you have r comma theta, and -r reflects across the origin, and the negative theta means we start at the pole axis and we go clockwise instead of counterclockwise. Now, an interesting fact is in our Cartesian coordinate system, every point has only one representation. So the point 23 is graphed as the point 23 every time. But if I were to give you this point in this polar coordinate system, let's do it over here. So we have a couple options here. First of all, 1, 2, 3, 4. Our radius is 4. So this could be 4 pi. And we have coterminal angles, so it could be 4, 3 pi. It could be 4, 5 pi. It could be 4, negative pi. 4, -3 pi. So because of our coterminal angles, then we have to remember that it can be written in several ways. The easy way to write that would be to say 4, and then our polar angle would be pi plus 2 pi n, because that says it happens for any integer. So that's the easy way to do it, where n is an integer. So that represents all of those and everything that could be imagined. It could also be the -r to go with it. So if we had here, we could call this -4, 0. So it could also be -4 pi plus pi times 2n plus 1. Because we have to add one it's not in the same spot. So your generalization is you could always do r and theta plus 2 pi n. Or we could have -r and theta plus 2n plus 1 times pi. This is your most common right here when we work in the positive r, and we work with it accordingly. So the connection between the polar and the Cartesian coordinates can be seen. Let's look at that. Now, if you were to sketch these on a normal plane, we would tend to set it up like this. And let's say we have 3 and 5 pi over 6. So that means we would come over here close to the end and put a dot, and we'd say 5 pi over 6 with a radius of 3. 3, 5 pi over 6. So you can see that you still get the same idea. They kind of draw them hanging in your book, but this is a better approximation, kind of gives a plan. It also helps you see how it ties kind of into the Cartesian coordinate system. But you can see the same axis lines here on this polar system, because here we have our axis lines where the top is pi over 2 and the bottom is 3 pi over 2. So it ties in together. So let's talk about if we have a Cartesian coordinate system. So here we have x and y. And I'm only going to look at the first quadrant for a moment. So we have some triangle here. Is this looking like a little bit of trigonometry that you should know? So if we have some triangle here, here's my x value and here's my y value. This x represents the x-axis. Then I know I have some radius on my unit circle. Well, I call it a unit circle, but we have some radius and some angle theta. Now this point right here, we're used to seeing xy, but it's also the point r theta. You see how the two match? They go together. That's why in trigonometry, some of you learn that cosine theta equals x over r and sine of theta equals y over r. So then we can find that x equals, multiply the r up, x equals r times cosine of theta, and y equals r times sine of theta. Now this looks like it happens only in the first quadrant, but it's true for all theta that we can work with. So since we have these, then it's easy to see that tangent theta equals sine theta over cosine theta, which equals y over r over x over r. So it's y over x. And then we find, like we saw earlier, that, let's write up here, that x squared plus y squared equals r squared, which is our equation for our circle, but they come directly from all of this concept. So the next concept is to convert, let's convert 2 pi over 3 from polar to Cartesian coordinates. So you need those formulas we looked at a minute ago, where x equals r cosine theta and y equals r sine theta. So r is 2, so we're going to say 2 cosine of theta, which is pi over 3. Now I use triangles when I do these. So your smaller angle is pi over 6, and it's 1, and pi over 3, and it's square root of 3, and then this is 2. So the cosine, we put theta in here for pi over 3. We don't need a theta. The cosine of pi over 3 means adjacent over hypotenuse, which is 1/2. So we have 2 times 1/2, which is 1. And then y equals r, which is 2, times sine of theta. We can use the same triangle. So sine of pi over 3, let's write that in here, sine of pi over 3. So sine of pi over 3 is the square root of 3 over 2. So y equals the square root of 3. So in Cartesian coordinate system, this point is 1 square root of 3. So let's look at it on the polar coordinate system. So our radius is 2, so we're going to go to the second circle. And we're going out to pi over 3. So that would be here. So if this is pi over 3, we'd go out to 2, and that would be what we have. So here's theta in here. Now, if you look at your Cartesian coordinate system, it doesn't directly fall in there, but think about the fact that it's in the first quadrant, and we go over 1 and up a little more. So we're looking at approximately the same thing. The next concept says represent the Cartesian coordinates in terms of polar coordinates. So this is our Cartesian coordinates, and we need to change it to polar coordinates. So what you have to think about is here I'm in my triangle, and -1, +1 is in this quadrant. So as you did in trigonometry, you're going to use the same concepts here. So this is -1, and this is +1, and this is theta. My picture's a little small. Let's do that a little bit better. So this is -1, this is +1, and this is theta. And we're looking for what theta would be. So we're going to say tangent is opposite over adjacent. So we can say tangent of theta equals opposite of 1 over adjacent -1. So this means that this happens, our reference angle here is pi over 4. And we're in the second quadrant. So that means that theta is 3 pi over 4 because it's just shy of 1. We know it's in the second quadrant for two reasons. Tangent is negative. So that means second or fourth quadrants, but we're in the second quadrant. And a tangent of 1 is pi over 4. So we know that we have this. Now let's talk about r. In order to find r is the hypotenuse here. So we can say r squared equals 1 squared plus -1 quantity squared. Now to solve for r, eventually we're going to take the square root. So I want you to keep that in mind. So we say r squared equals 1 plus 1. So r is the square root of 2. Now we have a formula for r, and it says r equals the square root of x squared plus y squared. So we don't actually have to draw it every single time. And they tell us that the formula for tangent is y over x. So those are our two formulas. To change from polar to rectangular, from rectangular to polar, you have r equals the square root of x squared plus y squared, and tangent of theta equals y over x. So these are your two formulas to go back and forth. Now this specific answer would be r, which is the square root of 2, and then theta, 3 pi over 4. So that's what we get when we change this given Cartesian coordinate system ordered pair into polar coordinates. This is our answer if we're within 0 and 2 pi. But since we are in the fourth quadrant, or the second quadrant, we could also add 2 pi to it and say the square root of 2 and 11 pi over 4. And come up with other answers. But this is the first answer we got is your best answer. It is a positive r, and it is in between 0 and 2 pi. So that's our best answer. Now the graph of a polar equation is r equals f of theta. Or you can say f of r theta equals 0. And this is all the points P that have at least one representation that look like this, r theta, that satisfy the equation. You're used to that. You're used to xy. You're used to the notation where xy satisfies the equation ax plus by equals c. So it's the same type of a format there. So this next idea says, what curve do we have when we have r equals 2? So if you think about r equals 2, let's pull in our polar coordinate again. I like polar coordinate graph paper. It makes sense. So if you start here with your origin and you label your pole axis right here, then r equals 2 starts here, and it's all of these points all the way around. It doesn't matter what theta is, r equals 2. So that means I have a circle here where r equals 2. It has a center at 0 and a radius of 2. So this is r equals 2 here. So let's say we had r equals 4. We'd have a circle with a radius at 4. If we had r equals 1/2, we'd have a circle with a radius at 1/2. So whenever you have an equation that says r equals, we get a circle if it's just r equals. So what if we just had theta equals? So the red is r equals 4. Let's talk about theta. let's say let theta equal the number 2. Let's go back to the number 2. So if theta equals 2, that means we have a line at 2. Now think about the fact that this is radians, because usually it's pi over 2 or something like that. So 2 radians, that means I need to approximate. Now that's in between pi over 2. Pi over 2 is 1.57 radians, 1.571, and 2 pi over 3 and 2 pi over 3 is 2 point, I lost my decimal, 094 radians. So it's somewhere in between these two. So just for sake of argument, let's call this line 2. So I should get a straight edge. So this is theta equals 2 right here. And you're thinking, why did you go through? Stop. This is the point 1, 2, 3. This is the point 3, 2. This is the point 5, 2. These are a little hard to read. Let's try again. This is the point 5, 2. This is the point 3, 2. This right here is the point 1, 2, negative 2, 2. This is the point negative 4, 2. So that's why it goes through. So if we had theta equals pi, let's not use pi. That's a little, let's say theta equals pi over 4. Remember, we're in radians. So that means that it goes right through the middle here. And the other way. Now your calculator isn't very helpful here. If you go to the mode button, like we talked about last time, and make sure you're in radians because we work in radians, and then go down to the type of graph, you're going to go to the polar. So the first one is function, the second one is parametric, the third one is polar. Let me see if I can pull this in for you. So you're going to go to the mode button, and then you're going to choose polar here, but make sure that you're in radians. So polar and radians. Now when you do that, when you hit y equals, you're just going to see /R1 /R2. So you could put in a radian of like 4, and then go to your zoom and do zoom square. And you'll see that your circle happens with a radius of 4. But it's not going to graph nearly as helpfully as your calculator did for parametrics. So keep that in mind. The next problem says, sketch a curve with the equation r equals 2 cosine theta. Now, before you play with your calculator, let's talk about this curve. So we form an XY chart, but instead of XY, we're going to have a theta and r equals. So remember, r is 2 cosine theta. So we start with theta, and we're going to go 0, and let's go pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. Now we'll see what's happening before we go back and decide whether or not to continue. So if we put in 0, cosine of 0 is 1 times 2 is 2. Cosine of pi over 6 is the square root of 3 over 2 times 2 is the square root of 3. Square root of 2 over 2 times 2 is the square root of 2. 1/2 times 2 is 1. 0. Now remember, cosine is negative in the second quadrant. So 2 pi over 3 is negative 1/2 times 2 is negative 1. Negative square root of 2. Negative square root of 3. And then negative 2. So let's look at this graph. Now it's easier to graph when r is on the left, because remember that our points are r theta. So I'm going to move my r's to the left. 2, square root of 3, square root of 2, 1, 0, negative 1, negative square root of 2, negative square root of 3, and negative 2. So I'm not going to draw the axis lines. They're here. Our pole is right here in the middle, our pole axis. And I'm going to say that this is 1, and this is 2, and this is 3. Because it's going to be easier to graph if we space it out a little bit like we did in a graph earlier. So usually your circles count as each one. We could do that. It's all right. Could have zoomed. 1, 2, 3. 1, 2, 3. These are negatives. So then we're going to plot the points. 2, 0 is right here. The square root of 3 pi over 6. Now this one's pi over 6. This one's pi over 3 because they get confusing. So square root of 3 is 1.73. And we're at pi over 6. So it's about 2. It's almost out to 2 right in here. And then we have, for pi over 4, we have the square root of 2, which is 1.414. And then for pi over 3, we have 1. And then 0, 0. And negative 1 is 2 pi over 3. So we come to 2 pi over 3, which is over here, 2 pi over 3. And negative 1 is down on the bottom of it. So here's the negative version. So we go here. And then at 3 pi over 4, that would be this mark right here. So at 3 pi over 4, we're going to negative 2. So over here. And then at 5 pi over 6, we are at negative square root of 3. So that's negative 1.7, and it balances out down here. Might have been closer, but that's okay. Sorry, negative 1.7 is about here. Oh, this was supposed to be 0.414 here. Let's do that one again. Remember the, right here, the 3 pi over 4? Right here, the 3 pi over 4 is negative 0.414. So it was almost 1.5. And then we have this. And then at pi, over here at pi, we have a negative 2, and it bounces over to match over here. So we start and end up at the same place, and it graphs to look like this. And then it comes back out. So let me highlight this with the red so we can see it a little bit better. And that's because the dots bounce down on the negative values. So this is what our sketch looks like. And then we're asked to find a Cartesian equation for the curve. So to convert it to a Cartesian equation, we're going to use the equations that we know, that x equals, let's do it. Let me see if we can put it in here. X equals r cosine theta, and y equals r sine theta. So we can solve this one. We want to change them to Cartesian, so we're going to say cosine of theta equals x over r, and sine of theta equals y over r. So when we take our given equation of r equals 2 cosine theta, we have r equals 2 cosine theta. Then that means that we can say that r equals 2 times x over r. So r equals 2x over r. So r squared equals 2x. Now we know from the other equation that r squared equals x squared plus y squared, or they call it x equals the square root of x plus y squared. Hopefully you see that these two are the same. So because we have this, we can say x squared plus y squared equals 2x. So x squared minus 2x plus y squared equals 0. So if we were to work with this further, we would find that x minus 1 squared plus y squared equals 0. I'd like to do it more for you, but that comes from completing the square. So we have a circle with the center at 1, 0, and a radius of 1. Thank you.